Welcome to the first lecture in AT3. If we just mark that up here. The lecture wants to explain what, in general, structural engineering really does or checks to buildings. And I've drawn a little building here, call it a church with the staircase and some bracing. And with all the loading applied to these buildings, what is it we have to, as engineers or architects, consider? And so I've done a little box here, and if we maybe at the first box, we just call that serviceability limit state. And then the second box again would be serviceability limit state. However, let's call that vibrations and accelerations. Well, the first serviceability limit state would really focus on static deflections. So we have to check those two boxes, and then later on a very big one would be the ultimate limit state. And for ultimate limit state, we could really say we have to make sure that the material and the member capacities are okay. And for that one, we need to look at forces, normal forces, shear forces, moments, and so on. And those ultimately give us stresses and shear stresses, and they are then related to material. And finally, something that's maybe a little bit less known to you guys, that would be stability. Now, stability could be a local or a global problem. And I'll explain in a second what that means. But it could be, for example, buckling of a column. It could be plate buckling or system buckling. Now, system buckling could be, for example, a sway to the side or a twist. So we have the stability, the ultimate limit state, and these serviceability limit states that I divide here in deflections and vibrations and accelerations. So here's our building. Let's do an example on what deflections means. Say we were to pick a certain slab here, which I'm circling in red, and I, for a second, create a so-called structural system. So instead of drawing this column here or these other three columns, I basically say I'm just looking at that slab and I give little supports where these columns hit the slab from the underside. And then I can say, okay, there is a certain system geometry to this, which we normally refer to L as a system length. So we would maybe have here L1. If this is the same as L2, L1, then it stays L1. And here we would have L2 a little bit less. Now with that established, we will have loadings to the slab. For now, and then we look at other loadings in a second, I'm just giving this little giggle here, which is supposed to be the dead load of the slab. That's the permanent structural concrete or steel weight. And also the finishes. In this case, we call that super dead load. And these are really acting downwards all along the slab. So instead of drawing all these arrows, that's the more complete symbol, and two lines, you can just make a little quicker model here. So what would be problematic here if we had deflections that were too high? Well, the reason we limit deflections is if we had partition walls here and the slab would really deflect a lot, the partition wall may crack or not stay in place. If we would have a curtain wall, a facade on the outside, and the slab deflects too much, maybe the joints will lose their water tightness, their air tightness, and we would have system leakage. And also, of course, if you say have a party and the slab deflects too much, it may scare people or everything rolls to the middle of the floor. It's basically no longer a good serviceability state. That's why deflections want to be limited. How do we limit deflections? Well, usually we don't want them to become too much in a absolute fashion, for example, half an inch at mid-span, or we say, let's define it as a ratio of the span over, for example, 240, maybe for a mullion, or 300, anything that makes sense with regards to the relative length of a system. And if we then actually draw these deflected shapes, and they depend, of course, on the span and where the supports are, we can go to these maximums. By the way, they don't necessarily always occur mid-span. It depends on the system and geometry. We can then say, okay, our slab needs to be so stiff that these maximum deflections, F, are still within acceptable limits, so that we're okay. I could have also chosen the same thing maybe on a vertical element. Say we have that tower here, and then this tower system might have a structural system simplified, which I'm drawing in a vertical way. And then if we had some wind loading coming from the side, which again say was like a linear load, we could also determine the deflection here and find the maximum of that wall, say. And then this deflection, we would measure it vertically. And again, make sure that that tower wall or that element is stiff enough so that these deflection under certain loads and load combinations don't become too large. So this would have been, like, for example, wind. This would have been dead load, or even both of them super dead load combined. Now, what are serviceability limit states when we look at vibrations or even accelerations? Well, think about a staircase where, like, a person here is walking on, and I just draw this person here very diagrammatically. And even though the staircase isn't going to break or isn't going to statically deflect too much, there could still be this bouncing up and down effect. This long span structure may have a vibration problem. And so what you do is you not only check the static deflection limit on these staircases, but you want to make sure that the so-called eigenfrequency, let's call the lowest frequency here frequency, say F1, has a certain range, and this is measured in hertz, 1/2 unit, doesn't really go to the same range of what a person normally excites when you walk up and down a stair, and that's maybe anything from 1.5 to 3-4 hertz. So as a structural engineer or architect, when you do very slender long span stairs or even floor slabs, see these floor slabs here could also bounce up and down if they were really long, that this in terms of acceleration and frequency does not worry the slab. Like if you had a dance studio there or a party